Here's an example of a static system and using vectors. Now, I haven't worked through this problem, so I'll be doing it as I talk. So here we have a support system on a building. It's holding on to a rope, and the rope is attached to this 250-pound object. We're going to ignore the weight of the rope, or we're going to add the rope into the weight of the object down here. Either way, the total is going to be 250 pounds. Now, it has to be in pounds because that gives you a force that's being pulled down. If you make it a mass, you have to change it into a force dividing by the acceleration. It's a little tricky. So here, I'm just going to leave things in pounds. And I know the measure of this alpha and the beta. The alpha, the small angle, is 20 degrees. The beta, the big angle, is 130 degrees. And what I need to do is figure out, as this force is being pulled down on this support system, what kind of vectors are going to be appearing. So one of the forces is going straight down. Okay, so that's an easy one. I can draw that. Straight down force. So here we're going to start it at the origin and go straight down. I'm going to make that a little thicker. There we go. Nice vector going straight down. And it's pulling with a force of 250, or its magnitude is 250. All right, now we just got to figure out what these other two supports are doing. So as the weight is being pulled down, the force is coming down. Oops. I gotta go back to my pen. The force is pushing down on this support in this direction. And if you know anything about physics, it's always opposite and equal reaction. So as the force is pulling down this way, the post is pushing back in that direction with the same magnitude. So we're going to get another vector that's pointing off, let's see if I can get the to be at least parallel in this direction. And I don't know what's magnitude, so I'm just going to draw the arrow random. All right, the same thing is going to happen with this other post. Now, as this thing pulls down, the force on the post is actually going in this direction. It's trying to stretch this post out as the weight pulls down. So that means the vector is going to be going in the opposite direction. So it's going to be coming down in this direction. So where that one is pulling up, this one is going to be pulling down to the left. Okay, so try to get that parallel. Something like that. Now I'm quite sure this one's a little more steep. Oh, I can't do it. Delete it. I think that one's a little more steep. Oops. Kind of like that. So what happens is, if this object is going to sit still, then the sum of these forces has to be zero. Has to be zero. So the force of the weight going down, the force of the pole pushing up, the force of this pole pulling it towards the building, they all have to add up to zero. All right. So let's give these things names. This one, I'm not even going to give it a name. It's literally just 250 J. Because it's going down, you might want to give it a negative. Another way of denoting that would be 0, negative 250. And that would represent the weight. So I'll call this W vector. Why not, for weight? The problem with these other two vectors is I really don't know much about them, but I do know their angles. So let's talk about alpha here. Alpha is 20 degrees, and it's literally between the building and the post itself. So this angle here is 20 degrees. So that forces this angle on the outside, because we always want to go to the positive x-axis, to be 70 degrees. So we know a little bit about this vector. It has a direction of 70 degrees. Now, if you want to get fancy, it's 20 degrees north, 20 degrees east, but we need the 70. All right, beta is here between the vector and the building. but we have to kind of figure out where it belongs in this picture. So this angle, I don't think that's what it's talking about, because that would be a very small angle. More than likely it's this angle now. If you draw the building on this side, it's going to become this angle. These two angles are alternate interior angles, and therefore they're congruent. So this angle, I really should do this in green. This angle here, from here to here, is 130 degrees. But again, that's not the angle that we want. We want from here to here. So it's going to be 130 degrees plus 90. So that angle is going to be 220 degrees. Okay. So a couple things we know. We know, let's call this one vector u. Let's call this one vector v. We know that u's angle is 70 degrees, and v's angle is 220 degrees, 90 plus 130. The thing we don't know is the magnitude of u, and we don't know the magnitude of v. To come up with these vectors, it would be really nice if we knew what these magnitudes were, because then I could find out what their components were. So we're going to have to go a direction of combining these three vectors, adding them up, setting them equal to 0, and we're going to have these two unknowns. We know everything else. We know w for sure, and we know the angles of u and v. The only thing we don't know is the magnitudes of u and v. Alright, let's write it all out. So we're going to have the vector u plus the vector v plus the vector w, and we want to make sure this equals 0. Now this 0 is kind of important. It's not 0 the constant, because these are vectors plus vectors plus vectors, which should be a vector. So this is the 0 vector, also known as 0, 0. Alright, so vector u is going to be the magnitude of u, and I'm just going to let that equal capital A. It just makes these double lines and all the symbols go away really nicely. And similarly, I'm going to let the magnitude of v be b. Alright, so this is going to become a, I'm going to write it componently, cosine of the angle, which is 70 degrees, sine of 70 degrees, and that would be u, plus v, which is going to be the magnitude of b, times cosine of 220 degrees, sine of 220 degrees. And then lastly, the easy one is vector w, which is 0, negative 250. And this has to equal the vector 0, 0. Just squeeze that in there. Alright, so now just a little foreshadowing. And I'm not going to show all of the steps, I just want to show you where things are going to come in. This is the I component, this is the j component for each and every one of these. So what I want to do is I want to combine all the I components and set it equal to 0, combine all the j components and set it equal to 0, and see what happens. So the I components are going to consist of a cosine of 70 degrees plus b cosine of 220 degrees, and then plus 0, which is really no big deal, and this will equal 0. It's a nice easy equation. Alright, the second equation is going to be a little bit longer, a sine of 70, and I like leaving the sines and cosines in here because they're exact values, but you could, if you want, change them into a bunch of decimals. Sine of 220 degrees minus 250 is equal to the second component up here, this 0 over here. Alright, so here's our two equations. The nice thing is this equation only has two variables, a and b. So I can solve for a in terms of b, and then just go over here and substitute in for a and solve this equation for b. So I'm going to do two steps here. This one over here, I'm going to solve for a. So a is going to equal negative b, subtract it over, cosine of 220, divided by cosine of 70. And please don't take 220 and divide it by 70 and then try to take the cosine of it. Your calculator won't like it too much. Over here, before I substitute this mess into a, well, no, I'm going to have to do that anyways. This is going to become negative b cosine of 220 over cosine of 70. There's a sine of 70 in the top. If I really don't want to write both of them, I can write tangent of 70. So this is going to become negative b cosine of 220. Sine of 70 divided by cosine of 70 is tangent of 70. Use some of those nice trigonomic identities. Plus this b sine of 220. And then I'm going to move the 250 to the other side. All right, now my goal here is to solve for b. So one trick I can pull is, well, factor it out. So if I factor out b, and I'm going to switch the order of this so the negative term is in the second position. So I'm going to write sine of 220 minus cosine of 220 tangent of 70. Oops, tan of 70. And this has to equal 250. So the last step is to take this ugly mess and divide it into 250. So I'm not going to write it down, it just takes up a lot of room. I'm just going to do it on my calculator. So 250 divided by parentheses, you got to put that in there, there's more than one term down there, sine of 220 minus, make sure you close off after the sine of 220 with a parentheses, minus cosine of 220 times tangent of 70. And that's it, right? Yep. And end the parentheses, and we get 171, almost exactly. So b, which by the way is the magnitude of vector v, is equal to 171. The measurement is pounds of force. So the V support, I forgot which one V was. The V support, this one here, I'm sorry, this one here has to be able to support 171 pounds of pressure going in that direction. Oops, pounds. Whatever. All right. Now that we have what B is equal to, we can substitute it in here and find out what A is equal to. By the way, this is going to be the magnitude of U, the other support, the one coming down in this direction. All right, so B is 171 pounds, so it's going to be negative B cosine of 220, and the parentheses, divided by cosine of 70. For a grand total of 383. So the post that has to hold more weight is the support that's coming down and attaching to the building here. So this support is holding 383 pounds, while this support up here is only holding 171 pounds. So when you construct this, you have to make this post a lot stronger than this one over here. I'd say about, what is that, 2? More than 2 times as strong. And that's how you solve a static system. And then if you want, you can come up with the vectors, but usually it's the poundage that matters.